So in the next couple moments, we're going to do 4 different sample problems that are different series and parallel, some basic series, basic parallel, and then a combination one. So let's start and jump in with the first one here. This is the first sample. So a series circuit has the following. It has a 9-volt battery. It has a current of 0.25 amps running through it. And then there are 3 resistors in it, a 10 ohm resistor, a 20 ohm resistor, and some unknown resistor that's the third one. So what I'm going to do is I'm going to draw a picture here. If all 3 of them are in series, here's one resistor, here's another resistor, here's my third resistor. And so I can label this as a 10 ohm, a 20 ohm, and then this one we don't know. I'm going to just label that as R3. What is that one? Then I can bring this down and attach it to a battery. So remember that a battery in a circuit diagram is the parallel lines that are not evenly, they're not the same length. One is shorter than the other. And I know that my total voltage here is going to be 9 volts. And I also know that the total current running through the system is 0.257 amps. Now, whenever I look at that, then can't we say that if we know the total voltage and the total current, can't we find what the total resistance is? So we can simply do Ohm's law, which is V equals IR. We can say 9 volts is equal to 0.257 times R. And when we solve for that R total, we're going to get a total resistance of 35 ohms. So this will have a total resistance of 35 ohms. But that's not what the question asks for. The question asks for what is R3, and we have to think back through and remember that, hey, when we put resistors into series, then the resistances add up and we get a bigger resistance. So we can take and say, hey, don't we know that a total resistance in a series circuit is really the sum of all of the resistors, R1 plus R2, oops, I'm off the screen, plus R3. So we can take then and say 35 is equal to R1, which is 10, plus R2, which is 20, plus R3, and solve for R3. So 35 minus 10, 35 or 25 minus 20, and we end up with a R3 value of 5 ohms. And so that's going to be my answer, that it is a 5 ohm resistor is the third one. So in the next one, what we're going to do then is take and put this into a graphic organizer and solve for a sample 2 that is them in series like that. So in this one, in this sample, the second sample that we're going to do, we have a series circuit where we have our resistors all put in series. We know it's that way because as soon as the electrons come out of the battery, they have to go through this resistor, then they have to go through this resistor, then they have to go through this resistor. There are no choices there. They have to go through each one of those to get to the next one. And the beauty of a graphic organizer like this, where I have my total voltage, my total current, my total resistance, and then I have my each V and I and R for each one of the resistors, 1, 2, and 3. The beauty of it is there are 2 different ways that we can solve this. When we look at it, we know that in series, our resistors add up. So we literally could add our resistors up. Or the other thing we could do is we know Ohm's law across the row, where we can say V equals I times R. And so we could solve this for I and then know that in a series circuit, remember our current is constant, SCC. So all of these currents are going to be the same, and then use VIR to solve across. So we'll do both of those. We'll just practice with both of those. If I take and I add these up, then I'm going to take 20 plus 10 plus 15. That's going to give me a total resistance of 45 ohms. So remember, big concept. When I want a larger resistance, I'm going to put my resistors into series because my total resistance will be bigger than any one of the individual ones. So the next thing I'm going to do then, I have to do V equals IR here. I'm going to take 1.125 and divide it by the 15. And that's going to give me a current of 0.075 amps. Then remember that in a series circuit, SCC, all of those are constant, so I can literally say this is 0.075, this is 0.075, this is 0.075, and now I can do VIR across the row. VIR here, take 20 times that, I'm going to get 1.5. Take 20 times that, I'm going to get 0.75. Take 20 times that, and I'm going to get 3.375. And then here's where these are really cool, because now that we have this V column, can't we double check ourselves? And remember that in a series circuit, all of the voltages add up. So I can take 1.5 plus 0.75 plus 1.125, and they all get that value for the voltage. So I know that I did that correctly. Now for the third sample, the parallel resistors get a little trickier, okay? So we can do it both ways. We can either add these up to get the final total resistance, or we can do VIR across, and we'll do both of them just to double check it. Most of the students prefer to do the VIR first, and the reason is because remember that you would inverse add these so that you end up with a smaller resistance value, and they don't typically like to do that on their calculator. So if I take 15 times 0.2, I'm going to get a value of 3. So then when I look at a parallel circuit, remember that PVC, our voltages are constant, parallel voltage is constant, which means that all of these are going to be 3, 3, and 3. And what that does is it allows me to do VIR, or Ohm's law, across the row for these two guys, which would be 0.6, 3 divided by 5, and then 3 divided by 0.2 is going to give me a value of 15. And then remember that in a parallel circuit, all of my currents add up. So my total current is going to be I1 plus I2 plus I3. So when I add these up, I'm going to get a value of 15.8 for my current there. So this is going to be amps, this is volts, and these are all in ohms. Then the easy thing to do next is to do VIR across here. So 3 divided by 15.8, and I'm going to get 0.190 ohms for that. Now, to double check that, remember that in a parallel circuit, my total resistance is equal to, so the 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And the way I would do this is I would take and substitute in then the 1 over RT equals 1 over 5 plus 1 over 15 plus 1 over 0.2. And I'm going to put this in my calculator by using the x to the negative 1 button, or by using the 1 over x button is typically, or I mean, you literally could just do 1 divided by 5, 1 divided by 15. So I'm going to take and do 5, hit that button, x to the negative 1, plus 15, hit that button, x to the negative 1, plus 0.2, hit that button, x to the negative 1. And then when I get an answer, remember that answer is 1 over RT. So I'm going to take my answer and I'm going to hit the button one more time so that it flips this guy to give me my RT value. And when you do that, you should end up with that 0.19 value for that. So notice again, there are two ways we could do that. We could have done that to begin with and gotten that. So done this 1 over values and then solved across all of the rest. Or we could take and literally solve over here and work our way back and then double check ourselves when we get to that. So in the next problem, what we're going to do is a combination then of the series and parallel circuits and putting them together. For this last sample, we have a combination circuit where we have a bunch of series and parallel resistors together. So notice that when I come out of the battery, once I get to here, the electrons have the choice to go through one of these two, which means that they are in parallel with each other. The same thing you can notice over here, that the resistors are in parallel here. Now, this set of resistors, though, once it comes back together, they have to go through this resistor, which means that they are in series with this one, which is then in series with this parallel set of resistors. What we're going to do is we're going to do a technique that is called packing and unpacking, or collapsing and uncollapsing the resistor. And the important thing to this is that you draw lots of pictures, because the pictures really help in solving these problems. And you'll see here in a second why those pictures become crucial to that. So the first thing that I'm going to do is I filled in just I randomly picked some numbers for these. So I said that this is a voltage on the battery that is going to be a 12-volt battery. That will be like your car battery. I'm going to say that my R1 value is 10, that my R2 value is also 10, my R3 value is 25, my R4 value is 5, and my R5 value is 40. So the first thing I'm going to do then is I'm going to collapse the ones that I see that are kind of easy. So if I were to draw that, I'd say, well, hey, I can look at these. Like I said, these are in parallel. So if I take those and I put them together into a resistor here that is going to be an R12, what is the value of that resistor going to be? So remember that whenever I have parallel resistors, that in those parallel resistors, I can say 1 over RT, or R12, is equal to 1 over R1 plus 1 over R2. So I'm going to have 1 over 10 plus 1 over 10 is going to equal 1 over R12. And then if I take and do the inverse of 10 plus the inverse of 10, and then the inverse of that answer, then I'm going to get an R2 value, 1,2 value of 5 ohms. So this is going to be 5 ohms. Then I have my R3 value here. So this is R3, which is the 25 ohms. And then lastly, I'm going to have another resistor here. I'm running out of space because I didn't give myself enough space here. This will be R45, right? So I'm going to have R45, and I'm going to do the exact same thing that I did here, where I have 1 over 5 plus 1 over 40. So maybe do that here. 1 over R45 is going to be 1 over 5 plus 1 over 40. And whenever I inverse 5 plus the inverse of 40 and then inverse my answer, I'm going to get an R45 value of 4.44 ohms. So this will be 4.44 ohms. And then that connects back to the battery. So there is a picture where I've just collapsed two of them at the same time. So I collapsed this set that were in parallel, then I also collapsed these guys that were in parallel into this one. And remember, when we're collapsing, it's essentially saying, I'm going to take all of those resistors, and if I were to take them all out and replace them with one resistor, what would the value of that one resistor be? So the next thing I would look at then is to say, hey, aren't all of these in a basic series circuit? So now couldn't I take and replace all of those with one resistor that I could either call like R1, 2, 3, 4, 5, or the same as saying that's the total resistance in the circuit, and then come down and connect to my battery. Now, what do I do with resistors that are in series? So remember that resistors in series, I literally can take and just add them up. So 1, 2 plus R3 plus R4, 5. So I'm going to add the 5 value plus the 25 value plus the 4.45 value, and I'm going to get a total resistance here of, where did I calculate that? 34.44 ohms for a total resistance. So that's going to be this, 34.44 ohms of resistance. And again, oops, I missed my second side of my battery there. So there is that. And I have a total voltage here, remember, of 12 volts. So that would be collapsing it down to getting the total resistance. Now, that helps us because on our table now here, we can fill in our total resistance of 34.44. Now you notice that it's not so basic as what we did in the earlier problems, where I can literally just add all these up, or I can take and do the inverse of the 1 over 40, 1 over 5. I have to do these step by step based on the pictures as I'm collapsing them down into a total resistance. Now, the cool thing about this is, to work our way out of it, we have to work our way back through the pictures back to the original one that we have. So I would look at this and say, hey, can't I take and calculate my total current here and say my IT value, because won't I use Ohm's law, where I can say V equals IR? So 12 equals I times 34.44, and that will give me what my total current is, and that's going to be 0.348. So I know that this guy is going to be 0.348. Okay. Now, again, it's not so easy as just saying, well, all the voltages are the same or all the currents are the same, because this is a combination circuit where it's sometimes the same and sometimes not the same because of the way they add up in the different series versus the different parallels. What I would do now then is I would take and I would look back up here onto this guy and say, well, hey, when I am looking at a series circuit, so all of these were in series, what is constant? The voltage or the current? And remember that our trick to that is SCC, series current constant. So whenever I unpack this one resistor back up into these three, I know that each one of these is going to have an I and a V. So I'm going to have an I1 V1, I'm going to have an I3 V3, and I'm going to have an I45 V45, because each of those has a current and a voltage. And if my series current is constant, then every one of those is going to have the same current. So 0.348, 0.348, and 0.348. And then can't we use Ohm's law, the V equals I times R, and solve for each of those voltages, right? Solving for each of those voltages. So this gets kind of cool here. So now if I solve each of those voltages, I'm going to end up with this voltage as being 1.74. This voltage is 8.70, and this voltage is 1.545. Now, the cool thing about that is, what do you know about voltages that are in series? Aren't all of those series voltages, don't they add up to give your total? So you literally could add 1.74 plus 8.70 plus 1.545 and get that total voltage that is 12. And I think when I did that, I got like 11.89 or 11.98, somewhere really, really close to 12. So it shows you that you're on the right track, and you can be double checking yourself as you go, so you don't finish the whole problem and like, where did I screw up? Like, you can at least see as you're coming through the problem. Now, what that does, looking at my table over here, I can't fill in anything yet, except notice that I have finished the 3 ohm resistor, the V3, I3, R3. So I can fill that in over here and say this has got to be 8.7. This has to be 0.348. Okay, what's our next step going to be? So the next step then has to be unpacking these 2 resistors. So I'm going to take this and unpack it over into here. Now again, remember, each one of these resistors, I'm going to have an I1 and a V1. I'm going to have an I2 and a V2. And if this is a parallel circuit, what is our trick on a parallel circuit? So I probably should make sure I put an arrow here that this is my SCC value, right? Now, if I'm coming back this way from here and I'm coming into a parallel circuit, remember that our parallel voltage is constant, PVC, which means that both of these will have a voltage of 1.74. 1.74. And again, now I can do Ohm's law to solve for what that I value is. So when I take 1.74 divided by 10, I'm going to get 0.174. And again, when I take 1.74 divided by 10, I'm going to get 0.174. And look at that. So now I have the values for the 2. I can plug that in, 1.74. And the I value was 0.174. And then my value for my 1, which is going to also be, let's see, 1.74 and 0.174. Now, we can again double check ourselves, because remember, in a parallel circuit, if the voltage is constant, what do we know about the currents? We know that the currents add up. So if I take 0.174 plus 0.174, I get 0.348, and I know that I did that correctly then. So lastly, we have one more to break out of that, and that's going to be this set of resistors. So I'm going to take this now and break it out over here into these, which will be, again, parallel voltage constant. And I can say there's an I5 and a V5 and an I4 and a V4. And what is constant in a parallel circuit? Our voltages. So I know both of these voltages have to be this one, the 1.545, 1.545. And now I can use Ohm's law to calculate those 2 currents. So I can take 1.545 divided by 5, and I get a value of 0.309. I can take 145 and divide it by 40, V equals I times R, and get a value of 0.0386. Hey, notice again, which one of these 2 branches is going to have more current flowing through it? It's going to be this guy, because there is less resistance. So electrons will follow the path of least resistance. So now that I have those, there's my 4 value. I can plug that in here and say the voltage was 1.545 and the current was 0.309. And I can plug the 5 value in here, which is a voltage of 1.545 and 0.0386. So notice that it's not as basic as doing what we did earlier. It is unpacking and packing or vice versa, packing and unpacking, or collapsing and uncollapsing. And your pictures become really, really important. If you don't draw these pictures, it makes it super, super, super hard. Now, the problem is not that hard to do. It just is tedious, where there's a lot of different steps. There's a lot of different easy math that you're doing, but you can, fortunately, there's scaffolding all in there that you can double check yourself as you go. And that is some sample problems on basic series, basic parallel, and a combination circuit.